Welcome to today's presentation. Today, we are going to talk about gravitation. As we saw in the previous standard, the gravitational force is a universal force. That means it acts not only between objects on the Earth, but also between any two objects throughout the entire universe. It's a fundamental force that governs how objects attract each other, regardless of where they are. Now, you might be wondering, how was this force discovered? Well, that's what we will explore next. We'll look into the history and the scientists behind its discovery, helping us understand how our understanding of gravity has developed over time. This sets the foundation for the rest of our study, linking the force that keeps planets, stars, and galaxies in motion to the principles we will learn today. Gravitation, as we have learned, is a fundamental force that governs the motion of objects. It was Sir Isaac Newton who discovered this phenomenon. The story goes that one day he saw an apple fall from a tree and started wondering about the reason behind this. He asked himself, why do all apples fall straight down, vertically? Why don't they fly off at an angle or horizontally? That's a great question. Newton reasoned that the Earth must be attracting the apple towards itself. This attractive force, which we now call gravity, must be directed toward the center of the Earth. If we think about the apple on the tree, the line from the apple to the Earth's center is vertical at that point. Because of this, the apple falls straight down, along that line. This understanding helped him realize that gravity pulls objects toward the center of the Earth, explaining why objects fall downward and not sideways or upward. This discovery laid the foundation for understanding the universal force of gravitation that affects everything on and around our planet. Let's take a closer look at this figure. On the right, you see an apple tree on the surface of the Earth. Now, the force acting on the apple, this is the force of gravity, is always directed towards the center of the Earth. Think of it as a straight line from the apple's position directly towards the Earth's core. This is what we mean when we say the force is along the perpendicular from the apple to the surface. Additionally, the figure shows the gravitational force between the Earth and the Moon. This is a crucial point because it highlights that gravity isn't just acting locally on the apple, but also governs the interaction between massive celestial bodies like the Earth and the Moon. It's important to note that the distances shown in the figure are not to scale. The actual distances between the Earth, the apple, and the Moon are vastly different. Understanding these forces and their directions helps us grasp the fundamental concept of gravity as a universal force acting along the line connecting two masses, whether it's an apple on a tree or celestial bodies in space. So Newton wondered, if the force of gravity acts on apples on the tree at different heights from the surface of the Earth, could it also act on objects much farther away? For example, like the Moon, which orbits the Earth at a much greater distance. This leads us to an interesting question. If gravity works on objects close to Earth, can it also influence objects even farther away? And not just the Moon, but other planets and the Sun itself. Essentially, Newton was thinking about whether gravity is a universal force that acts across vast distances in space, connecting everything in the universe. This idea was a huge step forward in understanding the fundamental nature of gravity as a force that can extend beyond our immediate surroundings and influence celestial bodies far away. It ties directly into the broader theme of how gravity governs not only objects on Earth, but the entire cosmos. Let's talk about force and motion. We've seen that a force is necessary to change an object's speed or its direction of motion. Basically, without a force, an object will keep moving at the same speed and in the same direction. Now, moving on to a key figure in this field, Sir Isaac Newton. He lived from 1642 to 1727 and was born in England. Newton is considered one of the greatest scientists of recent times because of his groundbreaking work. He formulated the laws of motion, the equations of motion, and his famous theory of gravity, all of which he detailed in his book, Principia. Before Newton, Kepler had already described how planets move through space with his three laws. But what was missing was an explanation for why planets move the way they do. Newton's genius was in providing that explanation. He used his law of gravity to mathematically derive Kepler's laws, showing a clear connection between gravity and planetary motion. So, in essence, Newton didn't just describe motion, he explained it. His work laid the foundation for understanding how forces govern everything from everyday objects to the planets themselves. This understanding is crucial as we explore the broader laws that rule our universe. In addition to his work on gravity, Newton made groundbreaking contributions in several other fields. He explored the nature of light, heat, and sound, uncovering fundamental principles that still influence science today. Notably, he invented a new branch of mathematics called calculus, which revolutionized the way we understand change and motion. Calculus has wide-ranging applications not only in physics, but also across various areas of mathematics. Another remarkable achievement was that he was the first scientist to construct a reflecting telescope, which greatly improved astronomical observations. All these contributions highlight Newton's incredible versatility and his role in shaping the scientific world we know today. Let's consider a simple experiment. Tie a stone to one end of a string. Now, take the other end in your hand and start rotating the string so that the stone moves along a circular path, just like in the figure. Now, here's a key question. Are you applying any force on the stone? Yes, you are. And in which direction is this force acting? It's directed towards the center of the circle, pulling the stone inward. This inward force is what keeps the stone moving in a circle. That's what we call the centripetal force. Now, how can we stop this force from acting? Well, if you release the string, the force is gone. The tension disappears, and the stone is no longer pulled inward. What happens then? The stone will no longer follow a circular path. Instead, it will fly off in a straight line tangent to the circle at the point of release due to inertia. So, to summarize, when you're holding the string and rotating the stone, you're constantly applying a force towards the center, which keeps the stone moving in a circle. Once you let go, that force ceases, and the stone moves straight ahead. This simple example beautifully illustrates the concept of centripetal force and how it is essential for circular motion. When the stone is released from the string, it will fly off along a straight line. This line is actually the tangent to the circle at the point where the stone was when released. The reason is that, at that precise moment, the stone's velocity is directed along that tangent. You might remember a similar activity we did earlier, where a 5-rupee coin on a rotating circular disc flew off along the tangent. This helps us understand that whenever an object moves along a circular path, a force acts on it, directed towards the center of the circle. This force is what we call the centripetal force. It's essential because it keeps the object moving in a circle. Without this inward force, the object would fly off in a straight line, just like the stone or the coin. So the key takeaway here is that the direction of the velocity at the instant of release is along the tangent, and the force maintaining circular motion is always directed towards the center, highlighting the concept of centripetal force. This idea is fundamental in understanding circular motion in physics. When we hear the word centripetal, it simply means center-seeking. It refers to a force that pulls an object towards the center of a circle. Now, think about the moon, which is Earth's natural satellite. The moon orbits around the Earth in a specific path or orbit. During this motion, both the direction and the speed of the moon are constantly changing. This suggests that some force must be acting on the moon to keep it in that orbit. And what would be the direction of this force? Well, it must always point towards the center of the orbit, so towards Earth. If no such force acted on the moon, it would just move in a straight line, flying off into space rather than staying in its orbit. This idea isn't just limited to the moon. Other planets in our solar system also revolve around the sun in a similar fashion. They are constantly pulled towards the sun by a force. Can you guess what that force is? Yes, it's gravity. Gravity acts as the centripetal force here, always directed towards the sun, keeping the planets in their orbital paths. So, in summary, whenever we see celestial bodies moving in curved paths, there's a force, like gravity, that's constantly pulling them towards a central point, ensuring their orbit. From the activity, example, and questions we've discussed earlier, it's clear that for the moon to orbit around the Earth, there must be a force acting on it. This force is exerted by the Earth itself, which attracts the Moon towards its center. This gravitational pull keeps the Moon in its orbit, preventing it from drifting away into space. Similarly, the Sun exerts a gravitational force on all the planets, including Earth. This means that the Sun is constantly attracting the planets towards itself, which is what keeps them in their respective orbits. Essentially, this mutual attraction between celestial bodies is the core concept behind gravitational force, which is fundamental to understanding how objects move in space. So, in summary, the force of gravity is what causes the Moon to orbit Earth and the planets to revolve around the Sun, maintaining the stability of our solar system. Kepler's laws have a fascinating history that dates back to ancient times, when astronomers first observed planetary motion. Back then, all observations were made with the naked eye, which limited the precision but still provided valuable data. By the 16th century, however, astronomers had accumulated a significant amount of data about the positions and movements of planets. Johannes Kepler studied this wealth of information carefully. What he discovered was that planetary motion isn't random. It follows specific, predictable patterns. Kepler formulated 3 laws that describe how planets move around the Sun. These laws are fundamental because they marked a major shift in our understanding of the solar system, from a geocentric view to a heliocentric one, and they laid the groundwork for Newton's theory of gravitation. So, in essence, Kepler's laws help us understand the precise way planets orbit, which is crucial for astronomy and space exploration. They connect directly to the overall theme of how we've come to understand the universe through careful observation and scientific laws. Let's take a closer look at the ellipse. An ellipse is essentially the curve you get when a cone is sliced by an inclined plane. One of its key features is that it has 2 focal points, or foci. Now, what's really interesting about these foci is that the sum of the distances from any point on the ellipse to these 2 foci is always constant. So if you pick any point on the ellipse, say A, and measure the distance to F1 and F2, the total will be the same no matter which point you choose on the curve. The same applies to points B and C on the ellipse, where AF1 plus AF2 equals BF1 plus BF2, and also equals CF1 plus CF2. This property is fundamental because it links the geometric shape of the ellipse to the distances from these 2 fixed points, which is a key concept in understanding elliptical orbits and other applications in physics and astronomy. Remember, the focus points F1 and F2 are special because they help define the shape and properties of the ellipse, connecting the geometric to the physical. This idea ties into the broader theme of how shapes and curves are used to model real-world phenomena, such as planetary orbits. Let's take a closer look at Kepler's first law. It states that the orbit of a planet is an ellipse with the Sun at one of its foci. Now, what does that really mean? Well, unlike a perfect circle, an ellipse is more like an elongated circle or an oval. And in this case, the Sun isn't at the center of that ellipse. Instead, it's located at one of the 2 special points called foci. In the diagram, you can see how the planet moves along this elliptical path around the Sun, which is marked as S. This elliptical orbit explains why planets sometimes are closer to the Sun and sometimes farther away, affecting their orbital speeds. This concept is fundamental because it helps us understand the precise paths planets follow, which is key to predicting their positions accurately. It also connects to the larger theme of how gravity governs planetary motions in our solar system. Now let's discuss Kepler's second law, which is quite fascinating. Essentially, this law states that the line joining a planet and the Sun sweeps out equal areas in equal intervals of time. What this means is that when a planet moves closer to the Sun, it speeds up, and when it moves farther away, it slows down, but the area it covers over a given time remains constant. To visualize this, imagine the planet at position A and then at position C after equal time intervals. The distances traveled, marked as OB and CD, are different because the planet moves faster when it's nearer to the Sun and slower when it's farther away. Despite these differences in speed, the area swept out, like the triangles formed by these points, is always the same in those equal time periods. In the diagram, the straight lines AS and CS are drawn from the Sun to the planet's position at those specific times. These lines sweep out equal areas within the same time intervals, say ASB and CSD, which are equal in area. This constant area sweep is the core idea of Kepler's second law. So the key takeaway here is that the planet's speed varies depending on its position in the orbit, but the area it sweeps out over equal times remains constant. This principle reflects the conservation of angular momentum in planetary motion, tying into the overall theme of how celestial bodies move under gravity. Now let's look at Kepler's third law. Essentially, it states that the square of a planet's period of revolution around the Sun is directly proportional to the cube of its mean distance from the Sun. In simpler terms, if we take the average distance of a planet from the Sun, which we call r, and its period of revolution, t, then t squared is proportional to r cubed. Mathematically, we can write this as t squared times r cubed equals a constant, which we denote as k. Kepler discovered these laws by carefully studying the positions of planets through regular observations over time. What's fascinating is that he didn't have an explanation for why these relationships held. He simply observed the patterns. And this is where it gets interesting in the larger context of our study. These laws laid the groundwork that later helped Newton formulate his theory of gravitation. They were crucial pieces of the puzzle that led to a deeper understanding of how celestial bodies move in our universe.